All right, guys. So the last batch of notes that we talked about was on work. But before we really got into that, we discussed energy and how there's two different types of energy. There's kinetic energy, which can be calculated as kinetic energy equals mass velocity squared divided by 2. And then we also talked about potential energy and how potential energy can be calculated as weight times height, or specifically gravitational potential energy can be calculated as weight times the height of an object. And then if we put those two together, kinetic energy plus potential energy, that those two equal, when we add them together, they equal the mechanical energy, or the energy due to the movement of an object overall. We also talked about how the unit for energy is joules, and that unit is also used for work. And this is really because energy is just a measure of how much work can be done. And so if 100 joules worth of work is done, it takes 100 joules worth of energy to complete that work. Today, we're going to kind of move forward and talk about power and how power relates. So the first thing to understand is that power is really just a measure of the rate at which work gets done, or like how long it takes to get to do some work. And we can calculate this with the formula that power equals work divided by time. The SI unit that we use for power is watts, and you've probably seen this before, like on a 60-watt light bulb. That's simply a measure of how much power that light bulb puts out. Or a microwave is a 1,000-watt microwave, or a 1,200-watt microwave tells us how much power that microwave puts out. So when we take that formula, we fit it nice and neat in a triangle. Since work is up the top of our formula, it's what goes at the top of our triangle. Now the work has to be in joules, and the time has to be in seconds. And again, the power shows up as watt, or watts for plural. And if we think about this formula, we can increase the power of a person or of a machine by either increasing the amount of work that gets done or decreasing the amount of time it takes to do the work. If we do one of those two things, we're going to increase power. Now, if we look at, you had a couple of questions here on the right-hand side of your notes page that you should take a look at. The first, what is the power of a small motor that can do 4,500 joules worth of work in 25 seconds? So take a second, pause the video, complete this question, and we'll come back and take a look. Alright, so assuming that you paused the video, completed this problem, this is just a pretty straightforward question. Power is work, 4,500 joules, divided by time, 25 seconds. 4,500 joules divided by 25 seconds equates to 180 watts. That's how much power this small motor would be able to put forward. You have another question, which is in 8 seconds a box pushed 10 meters across a room with 40 newtons of force. What is the power? So take a moment and jump into this question, pause the video, but understand that this is a two-part question. So pause the video, complete the question, and then come back. Alright, so assuming that you paused the video, completed this problem, the first thing that you need to look at is that you are not provided with the amount of work that gets completed. You need to calculate that first. So you take your 40 newtons of force and multiply that by the 10 meters of distance, because work equals force times distance. So 40 newtons times 10 meters, that's 400 joules. So there's 400 joules worth of work done. Now you take that and apply that to your power formula. That power is work, 400 joules divided by time, 8 seconds. So 400 joules divided by 8 seconds, that's 50 watts. So in this case, 50 watts worth of power were utilized, or the power was 50 watts. So that's really the gist of power, but it lends itself to power and work together kind of lends itself to the idea of a machine. Now, when we think of machines, we think of like big complex machines like car engines and microwaves and who knows what else, but lots of big machines. When we're talking about machines this year, we're really talking about just totally simple, basic machines. And so the most basic definition for what a machine is just that a machine is a device that makes work easier by changing the size and or the direction of the force that needs to be applied. So this is a picture of a Rube Goldberg machine, which you may be familiar with. Rube Goldberg machines. They're just really complicated devices to do simple tasks. So in this case, it's just kind of a neat little picture. The goal of this whole machine is simply to press the power button on the TV, but it requires a whole lot of things to happen before it gets there. But when we think about actual simple machines, an example here is just a ramp. And a ramp is an example of a simple machine called an inclined plane. Now, it's important to understand that machines do not increase the amount of work that gets done. They're simply not able to do more work than the person that's using the machine. So in this case, we look at the force that a machine supplies, so the force that this ramp supplies, which is the amount of force needed to lift the boxes up into the back of this vehicle. That force is called the output force, or sometimes it's referred to as the resistance force or the load. This is the amount of force that the machine pushes or pulls with. The amount of force that the person supplies, whether it's a push or a pull, is often referred to as the input force or the effort force. And those words become very important. You need to know that input and effort are synonyms with each other, and output force, resistance force, and load are all synonyms for each other. So when this gentleman uses this machine, instead of having to put in the full amount of force to lift these boxes, this maybe half a meter it is up into the machine, into the van, he can supply a lot less force to use the ramp, but instead of only moving the boxes half a meter, he has to pull over this full maybe 2 meters worth of distance. So he's able to supply less force, but he has to supply that force over a greater distance. This makes the work feel easier, but it actually does not decrease the amount of work that gets done. And so we kind of then follow this with, do machines have to have moving parts? And when we talk about simple machines, the answer to that question is resoundingly no. Simple machines like the head of an axe is an example of a machine called a wedge, and it does not have to have moving parts. A doorstop is another example of this. We already talked about the idea of a ramp, which is an inclined plane. The machine, the ramp itself, doesn't move. Or a screw, or a broom is actually even a simple example of a simple machine called a lever. These are all simple machines where there's not moving parts. The whole device might move, the whole machine might move, but the part doesn't have separate parts that move. Now, there are two types of work that occur whenever we're talking about using a machine. There's the work input, and this is the work that you do. It's calculated as your force input multiplied by the distance input, or the effort force times the effort distance. And that's shown here at the bottom in blue, where force sub I, F sub I would be your input force, and D sub I would be input distance, or F sub E would be effort force, or effort distance for D sub E. So that's the work that you do. And then there's the work that the machine does, and this is our output work, and it's our force output times our distance output, or our resistance force times our resistance distance. So these are ways that we can calculate these two different types of work. Now, in an ideal world, the amount of work that you do, your input work, would be exactly the same as the amount of work that comes out from a machine. Now, we need to recognize, we all know that we don't live in an ideal world. We live in a world where there's friction. So some of the work that you do when you use a machine is going to be converted to thermal energy and not work output. So in reality, when you use a machine, even though a job might feel easier, in the real world, you're actually doing more work than the machine does. You get less work out of the machine than the work that you put in. Again, if we're talking about an ideal world, a frictionless world, the input work and the output work would be exactly the same. So machines do not increase the amount of work that gets done. They're never able to output more work than what is put into them. And this is kind of another quick way we can take a look at this. So if we have this first gentleman here pushing a barrel up a ramp, he's pushing with a force of 25 newtons, and he's pushing over a distance, the length of the ramp, of 3 meters. This means he's doing 75 joules worth of work. The other gentleman over here, he's lifting the barrel straight up from the ground. He's not using the ramp. So in this case, because he's lifting the barrel, he's having to supply 75 newtons worth of force, rather than the ramp helping him with that force. But he only has to lift the barrel for 1 meter of distance straight up. He doesn't have to worry about the full length of this ramp. So it's also 75 joules worth of work, same as the gentleman that's using the ramp. Now really, this guy that's lifting the barrel straight up, he's doing the same work that the machine itself is doing, lifting the barrel 1 meter into the air and setting it on the table. This shows that the amount of work done by the machine, the ramp, is the same as the amount of work done by the person using that machine. So our input work, what the guy is doing here using the ramp, is the same as the output work, what the ramp is doing to lift a barrel straight up off the ground. So who's doing more work? In this case, both guys doing the same amount of work, which is the same as what the machine is also doing. This whole idea comes down to what's called the force-distance trade-off, which is really conceptually just the idea that a machine can either increase the distance over which a force is supplied, but utilize less force, it can output less force, or the machine can decrease the distance over which the force is supplied, but supply a greater force. These are the two things that a machine can do. So when you use a machine, the machine is always going to take your force and your distance, and it's going to move those two in opposite directions. So if the machine increases force, then it decreases distance. If the machine decreases force, then it increases distance. And we call this the force-distance trade-off, that you're getting more force out of the machine, but you're getting that force over a smaller distance. Or you're getting less force out of the machine, but the machine is supplying that force over a greater distance. In one way or another, it should make the work feel easier. If it doesn't make the work feel easier, then we wouldn't utilize the machine, but it doesn't actually change the amount of work that gets done. It simply changes how it feels to do that work. Alright guys, hopefully that clarifies some things for you. If you have any questions, make sure you shoot me an email or stop in to see me.